Alright guys, so the topic for today is CPU scheduling. So we're going to talk about different techniques on how you can schedule tasks in the CPU. Okay, there are quite a lot of techniques. I try to cover as many as possible. Okay, so you're aware of all the examples. This lecture is actually going to be let's say not very code demanding. We're going to talk more about the logic, how processes work together, how they are scheduled, how they are dispatched, and so on. Okay, so let's jump right into it. Okay, so as we talked in our previous lectures as well, obviously, if we imagine that we have a single processor system, we don't have just one task running there all the time. So let's say if a task takes too much time, sometimes it is swapped, and also sometimes the tasks are using different components of your computer. Sometimes they're using the CPU, sometimes they can use an input-output device, and so on. Okay, so we need to have some techniques with which we can make the CPU more useful and to use its capacity on maximum. So what do I mean by this? So let's say if we have a process that, and you know, a process is just a program that is getting executed inside our system. So let's say at some stage our program, or our process in that case, wants to access the CPU. In that case, we're having a CPU burst, which means that the program is executing the CPU. Okay. At some other point, the same process might want to access an input-output device, right? Or it might wait for input-output device. So while this process is waiting for input-output device, instead of not doing anything with the CPU, obviously what we want to do is to swap this process with another one while it is waiting for the particular input-output device, or it's waiting for a critical section to be assessed. Okay, so in order to be able to implement that, we need CPU scheduling. Okay, and here you can see on this graph on your on the left side, my left. Okay, so here how we can wait sometimes, and while this wait for the input output device, obviously we want to run another process so we don't waste the CPU execution. Okay, and obviously the more frequently we swap between different, so the more the higher the burst duration it is, okay, the less frequently we can switch between different processes. Okay, so if the burst duration, or the time that it takes for a process to complete in the CPU, is less, this means that we can swap between processes more frequently, and we can obviously execute more processes. All right, so in the CPU we have two types of schedulers. One of them is the short-term scheduler, okay, which takes the tasks from the processes from the ready queue. So the ready queue has all the processes that are ready to be executed from the CPU. Okay, and you're probably familiar with this graph right here. Okay, this shows the different states of the process. Okay, so when a process is created, it becomes new, right? Then it can be accepted in the ready queue, waiting to be executed. It might wait for input-output device, or from the ready queue it can also be running. Once the process finishes, then it can go to terminated state. Obviously, if the process needs to assess input-output device or do anything else, we're going to wait for that particular device, and meanwhile we're going to simply execute other processes inside the CPU. So now One very important thing when we are scheduling things inside our CPU is whether we're going to do it in preemptive or non-preemptive way. So I have a question: what is preemptive and non-preemptive scheduling? Any ideas? Yes. Close, close. And what would be then preemptive? Or did you say about? I said preemptive. Okay, what is then non? Okay, I would say it is probably the opposite. So if the execution is interrupted, what it is, preemptive or non-preemptive? It's preemptive, yeah. So if we're more dynamic, okay, and we're interrupting the execution of a process, then we have preemptive scheduling. So you can imagine this as non-preemptive. Preemptive means that a process with higher priority is going to wait until process with lower priority finishes, and then it will take the resource. Preemptive means that the process with higher priority will immediately take the resource. And once that happens, if the previous process in some critical section, this would mean that the previous process will make the critical section available, and it will pass the control to the process with higher priority. So obviously, non-preemptive means that the algorithms will be less complicated because we don't just block processes to run others. But preemptive scheduling would mean that our system will be way more responsive, okay? Because we're not going to wait until some process completes before starting another one. Okay, so one component of the CPU, this is the dispatcher. Okay, so the function of the dispatcher is to give the control of the CPU to a specific process. Okay, so when we want to change what process runs in the CPU, okay, the dispatcher takes the process selected by the scheduler, okay, and runs it inside the CPU. Okay, so the dispatcher is the actual tool that is able to switch the context from one process to another, to switch to user mode, to kernel mode, to jump from one location to another one. Okay, this is what takes the process and runs them inside the CPU. And the dispatcher latency is quite important because this is the time that takes the dispatcher to stop one process and starts another one, okay? And obviously this time is going to be added as processing time, right? So you can imagine that the more we switch between different processes, the more dispatcher latencies or dispatcher delays we're going to add. So we really need to think for algorithms that are going to be optimal. If we're doing too much switching, we're spending too much time for the switching itself. So let's say if you have processes that run for 10 milliseconds, but you decide to switch every 1 millisecond, this might be not very efficient because the dispatch latency might be just too great and there might not be any point to switch so fast, okay? Because you're going to get more delays. Okay, so here I wrote some of the criterias that we take into consideration when we want to schedule processes for the CPU. So the first one is the CPU utilization. This means that our goal always is to use and to keep the CPU as busy as possible. You don't want process to be waiting while your CPU is not working on very high rate. Okay, normally in the operating systems and the devices these days, they aim the CPU to be utilized from 40 to 80%. Okay, this is a good CPU utilization. And if you have too many tasks waiting, but at the same time your CPU is utilized at 10%, obviously this is going to be a problem of the operating system, and this would mean that you're definitely not doing enough load balancing between the different cores, or something else. But we're going to talk about all of those. Okay, then we have the throughput. Okay, so this is a number of processes that complete their execution for a certain amount of time. Okay, obviously, if we measure how many processes started and after 10 minutes how many processes completed, this will be the process throughput for the time frame of 10 minutes. So this is another measure, another criteria the scheduler can have. The scheduler can have the goal to complete, let's say, 100 processes for 1 second or 100 milliseconds. Okay. Then we have the throughput time. This is the amount of time to execute a particular process. Okay. So when we know the amount of processes that we executed, okay, and when we divided this by the total time it took us to execute those processes, we can find the average time that it took us per process. Okay, it's pretty straightforward. Waiting time is very important, and this is the amount of time that the process is waiting in the ready queue. Why is this time important? So sometimes in the operating system we can have processes that move between different queues. If we don't have that, then the processes with higher priority will always get executed, and the process with lower priority might never get executed if high priority processes keep coming. Okay, so let's say sometimes we have a rule in the scheduler that the process that will take longer should be the lowest priority. Firstly, we need to execute the ones that are executed quickly. But if we just keep this that way, if processes that are executed quickly are keep coming, then we will never execute the longer processes. So what we can do is that we can measure for each process how much time it's been waiting. If it has been waiting for too long, then we move it to a queue with high priority and we eventually execute it. Okay? And the response time is the amount of time that it takes from when a request is submitted until the first response is produced. Okay, so this is how fast the system responds to the action done by the process. Okay, so for example, I have a robot and one process wants to move the arm of the robot. How much time it takes from the completion of the process until the arm is actually moving. Okay, this is the system response time to the process. So I'm showing you those because by those criteria we can add some rules with which we can schedule the processes. Okay, and based on those criteria we always want maximum CPU utilization, maximum throughput, okay, minimum turnaround time, okay, minimum waiting time, and minimum response time. So everything related with time, we want it lower so everything happens fast. All right, so now we're going to look at some strategies, okay, to schedule tasks in an operating system. Okay, so the first and the most basic one is first come, first serve. Okay, so in that methodology, the processes are getting served whenever they come to the scheduler. So let's say if we have 3 processes, P1, P2, and P3, and P1 takes 24 seconds, P2 takes 3 seconds, and P3 takes also 3 seconds. What is going to happen is obviously P1 is going to run first from 0 to 24, then P is going to run second from 24 seconds to 27 seconds, and P3 from 27 to 30 seconds. Okay, so in that case, we can easily calculate the average waiting time for the process in total, right? So P1, since it executed first, how much time it was waiting? how much time P1 waited to start execution. Exactly. So P1 is obviously not waiting at all, since it starts immediately. Okay. So in that case, P2 is going to wait how much time? 24, because the time of the execution for P1 is 24 seconds. Okay, and then P3 is obviously going to wait whatever it takes for P1 and P2 to complete in order to start. So in that case, the average time, if we combine all of those numbers and divide them by 3, first grade math, 17. So on average, the process in our system waited for 17 seconds using this methodology. So then I'm going to ask you, is there a way for us to improve the average waiting time? Like, what would you do with those processes to improve the average waiting time? What do you think? In parallel? In that case, we cannot do yet in parallel. Let's say this, but a good one, good try. If we do in parallel, yeah, that would work, but let's imagine that we have a single core at the moment. Okay, yes? Okay, another good attempt to try, but we still don't have any preemptive algorithms applied. So we cannot do that. Okay, just think, guys, about the fact that I'm not asking you how to reduce the average burst time. We cannot reduce that. I'm asking how to reduce the average waiting time. Okay, how much the process wait to start executing. So what we can do with those three processes to do that? What criteria we can add in order to make those execute or wait less? So burst time is the time that it takes for the process to run inside the CPU. So once the burst time completes, the process terminated. Yeah, exactly. So that would help, right? Exactly, exactly. So this is exactly what we need. So if we do that, right, let's say we have this criteria. So those processes they arrive at the same time. Let's say P1 arrived a little bit earlier, okay? Um, then P2, then P3. So if we decide, okay, we have this algorithm that we want the process with shorter burst time to run first, right? So since those two, they have the same amount of time, we're just gonna use for them first come, first serve. So firstly, we're going to run P2 in that case, right? Okay, so P2 will wait 0. Okay, then how much? So then obviously we're going to run P3. P3 is going to wait how much time? 3 seconds. Okay, and then P1 is going to wait how much time in total? How much?
3 more.
3 more? Yeah, exactly. So 6 more. Okay. So 3 plus 6, 9 divided by 3. Okay, it's going to be on average 3 seconds the process will wait. So we just reduced the average waiting time from 17 seconds to 3 seconds, right? All right, and this is just okay. Okay, so exactly what we discussed right now, it is done here. So obviously, just like how we did it, if the first process, if we, so in that case, let's say if P2 comes first, then P3, then P1, obviously, the average waiting time is going to be 3 seconds. So if we choose the shortest first, we're going to have some advantage. And this is exactly what the next algorithm is doing. So the first one was first come, first served. And the one that you figure it out, guys, is shortest job first. Okay? So this is exactly an algorithm where we measure the burst time of the processes and we run those with less burst time first. Okay, so what issues we might see with this type of scheduling? So the first issue that doesn't come initially to mind, this is the issue with measuring the burst time. Okay, so sometimes if the processes have way too short burst time, the time that you take to measure it, it might be close to the time that it takes to run it in the CPU, right? So this is the first issue we might have. However, to overcome this issue, yeah, so this is the algorithm, right? We already talked about this. This is just another example. So we take firstly P4 because it has shortest burst time, then P1, then P3, and then P2. Okay? Okay. So we can. Okay. So I don't want you to remember this equation. Okay. But what it displays. So even if we don't know the actual burst time of the processes that are coming to us, okay, we can analyze what happened in the past, and we can analyze how our system and the programs behaved in the past. Okay, so obviously so we know that the process is pretty much a program in execution. So if you know that this program ran in the past and took 1 second, the chances that with the same CPU and exactly the same code, you're going to run for exactly this time, okay? So what you can do is once your system runs for some time, you can analyze whatever is recorded from the past and have some information and assumption about how the different processes are going to behave. So based on that, you can schedule them based on the assumed burst time. Okay, and this is when we implement the formula. So if you have processes with different burst time, okay, we can estimate for each process what the burst time is going to be, and you can see that with this algorithm we can actually get pretty close. Okay, so these are the guesses, and this is the actual data. Okay, so now the next thing that we're going to do is talk about some preemptive methods to schedule processes. Okay, so preemptive means that if a process is too long, another process can take over, okay, and then the initial process might be able to continue. Okay, so as we said, preemption might cause issues with having to implement more complex algorithms, okay, because if you stop a process, a critical section might need to be locked, okay, and so on. So the positive thing is that we can actually save some time, okay. So the first algorithm that we're going to talk about is the shortest remaining time first, okay. And in this algorithm, so let's say we imagine we have those 4 processes, and here we're going to measure not only the burst time, but also we're going to measure the arrival time, okay. So let's say we start with process 1 that has burst time of 8 seconds. So once it starts, since it arrived first, it's executed, okay. But at second one, another process P2 comes, okay, and P2 becomes with higher priority, okay, because it executes only for 4 seconds, right? So since this process is going to execute faster than P1, then P2 is going to preempt P1, and it will take over the CPU. Okay, and it will start. Okay. However, at second 2, a process P3 is going to arrive to the CPU. And here, this process has burst time of 9 seconds. So what's going to happen is that P2 will still be with higher priority. So it will execute until it actually completes. Okay. So once it completes, okay, and while it's actually completing, at second trip, so 3 is before 5, right? At second trip, it arrived before. That has burst time of 5 seconds. So now we have a ready queue of 3 processes, right? Waiting for P2 to finish. We have P1 that has left 7 seconds. We have P3 that has 9 seconds left, and we have P4 with 5 seconds left. The algorithm chooses P4 since it has the lowest burst time, and it runs it. After this is completed, the algorithm will run P1 since it is with the next lowest burst time, and after that we're going to run the process P3 since it takes the longest time. Okay. That way we can use preemption in order to improve even further our times. And you can see how this is going to be calculated here, right? Uh, Once we get the waiting times for all the processes, we can divide them by 4, and the final waiting time is going to be 6.5 milliseconds. Okay, so the burst time and the arrival time in this case are in milliseconds. Okay, the waiting time is going to be equal to the start time, so when the process starts, minus the arrival time when the process arrived. Okay, so so far with algorithms we so far you saw that we change the priority of the processes based on their burst time, right? So this is how we assigned priority to some processes, I mean higher priority to some processes and lower priority to others. However, there are many different types of priorities and many different rules based on which we can add priorities, right? So normally, if the priority is closer to 0, this means that priority is high. If it's further from 0, this means that the priority is low. Okay, so here it comes some basic concerns when the process have different priority. So as we already said, the first issue is called starvation. And starvation means that some processes take over the CPU and some processes never get executed. Okay? In the algorithms that I just showed you, obviously, if too many processes that run short amount of time arrive, then the processes that take a long amount of time are not going to be executed ever. Okay? This is called starvation. And starvation can happen in many different priority types. So the solution for the one that I just described is called aging. Okay? So we can measure the time that the process is waiting, and if it is waiting for too much, we can actually run it before a process that has lower burst time. Okay, so here is how you can schedule processes with different priority. Okay, so let's say here we have 5 processes, we have our burst times, but now as you can see they have priorities. Okay, so which process are we going to execute first? Exactly, yeah. So P2 has a lower number, which means the highest priority. So obviously you can see that P5 doesn't have the shortest burst time, but since it just has higher priority in the system, it is going to execute first. So by having a specific priority variable, we can get away from specifically relying on the burst time to execute process, and we can actually add many different criteria into that, one of which is the time that they waited. So for example, we can estimate those priorities here based on how much time the process were waiting in the system, okay? And then we can execute them regardless that some of them have longer burst time. All right. Now, the next technique has nothing to do with priorities or anything like this, or waiting times. So, yes. Yes. So yeah. So you can add systems that are so you can add functions that are atomic, which means that they are seen by all the processes. Okay, and they just keep track on the process. For example, when you look in your task manager, right, you get some information about the different programs that are running, and the same is happening in the background for every single process as well. Okay, so the operating system has functions that keep track of that, right? And as I said, not all the information can be detected for every process. If the process runs too fast, the operating system might not be able to see how much, might not be able to get all the information needed, because until the information has been decoded, the process already completed. Right? So that's also possible.
I think that's why we do. I mean, my thought process was input to the process. Say it's the same process, but it's different inputs. How does it manage?
Oh, so are you talking for, so before that I said, let's say if a process before was running, let's say for 10 seconds, we assume in the future is going to run for the same amount. Yeah, so this is assumption, right? If you run it with different inputs, the system might have information that with those inputs it was running for this time. If it doesn't have this information, it is going to assume something that is wrong, right? Or it might be close, it might be far. But you can imagine this is like, imagine this as having laws, right? So for example, there is a law, the speed limit on the highway to be 65, right? There are definitely people that can drive better than others, and they can definitely drive with 85 without any issues, right? But you're going to put some general law, so then when you look at the rates of deaths on the road, they're lower, right? And you're gonna measure that, okay, when I put 65, how my death rate changes. When I put 85, how the total death rate changes. So it's the same with the process. So if I put this algorithm to assume the burst time of the process, are they actually running faster? Yeah, maybe they are. If not, let's change something, right? Let's change maybe the assumption that I do. So this is the whole idea. Of course, there are things that you cannot predict. The operating system cannot predict. Okay, so now the next algorithm is called the round robin. Okay, and this is a preemptive algorithm that is implemented regardless of any priorities. Here is how it works. We have a queue, a very large queue, okay, and the processes are served with first in, first out, okay. So instead of us running some process first, then preempted based on some rules, we're having a single rule for every single process in our system. The rule is we have specific time quantum, which is amount of time, and we are saying a process can run for this specific amount of time. It cannot run more in the system than this time. So let me just see if I have here their slide. Okay, so in that case, if the process has burst time lower than the quantum, it is going to execute and is going to complete. If it has higher time than the time quantum, then it will stop at the time quantum. So if the time quantum is 4 seconds, every process will run for 4 seconds. After that, the next one will take over. If the process that was running for the time quantum is not completed, it is put in the end of the queue. That way, every process gets a fair share of the CPU time. Okay, so let's see our example here. So obviously P1 is going to take a lot of time normally to run because the burst time is 24 seconds. So you saw that this is what exactly happened before, right? If uh, the P1 comes, then it just takes over, and this is unfair usage of the CPU. So how this looks like in when we implement context. So firstly, P1 will write and it will run for 4 seconds. Then we'll put P1 in the end of our queue. So obviously our queue is of 3 processes. So P1 now will lose the priority, will get the lowest priority. P2 will come. Since the time, the burst time is lower than the quantum, is P2 going to complete? Yes, right? So P2 is going to complete. P3 arrives, lower time than the time quantum. It is going to complete as well. Okay? So now we move to the queue. So we move to P2, we move to P3. Now it's time again to P1. So what P1 is going to do, it will run because it is now the only process in the queue. Obviously, the actual implementation of this algorithm is going to detect if there is only one process in the queue. So we don't just switch from one process to the same one, because if we do that, what is going to happen? Any ideas? So let's say a process arrives and we execute the process for 4 seconds, then we put it in the end of the queue, then we execute the same process. What are we going to lose?
I think we don't use CPU.
Exactly, we're going to use CPU time because some of the CPU time is going to be allocated for switching that we don't need. Okay? Okay, so the time quantum is actually very important. Okay, we need to choose this variable with and make very good measures when we do that. And here are the extremes. If the time quantum is way too high, then you risk a process to take over the CPU and not release it for a very long time. Okay, which will increase the average waiting times in your system. If the time quantum is way too short, this means that the percentage of switching of the total process time, so let's say if the process executes for 3 milliseconds, but it takes 2 milliseconds to switch, obviously we don't want to do that because we're wasting 2 milliseconds on every switch, right? So we don't want such a small time quantum. So that means that we really need to make sure that we have good measurements of our system. We know what processes are running in our system, and then we choose a time quantum that is going to, firstly, make sure that there's fair share of the CPU for every process, but at the same time that we're not spending too much time for switching between the processes. Exactly. Okay, and here is a graph. I'm not going to focus on this too much, but here is a graph of the turnaround time versus the time quantum. Okay, so let's say you can have those graphs when you design operating system to see when you increase the time quantum, what is the turnaround time of a process. Okay, so when you get lower turnaround time, okay, that's better. All right, so far we were talking about keeping processes in a single queue, but in fact, you can actually keep the process in the operating system in multiple queues. And those queues can have processes with a different priority, right? So for example, you can have a queue with foreground processes and background processes. So let's say in the foreground process queue, you can keep process that the user interacts with, and based on this process, the user feels that the system is more responsive. So you obviously want to execute those processes first, and this queue can be with higher priority. You can also have some background, or we can say there you can put some batch processes that take longer time, some job that is more heavy and needs to be executed for longer time. You can keep it in the background queue. So for each of those queues, you can also implement different rules or different technologies that we learned so far, right? So let's say for the foreground processes, you can use that our mechanism that we just learned, okay, the round robin, and have a specific time quantum for each process that will make them run very fast. On the other side, in the background queue, you can apply the first come first serve mechanisms, and there the process are going to be executed slower. Okay, so you can separate in that way depending on what do you really want from the process, and you can separate them in different queues. Okay, so uh, once we talked about the queues, there are also feedback queues. Okay, and what that means is that a process can actually move between different queues. Okay, so guys on behind, what do you think is the feedback queue? So based on what a process can move from one queue to another, what would be the reason? Any ideas? On what? So the different queues, they have different priorities, right? So let's say on the top queue we have one priority, on the second queue we have another priority, on the third we have different priority. So what would make a process to move from queue that is with lower priority to queue that is with higher priority? Yeah, that's a good one actually. Okay, so you're saying that the process from priority 3 is dependent on process on priority 1? Yes, yes, that's actually a good reason. That's true. Uh, yeah, they can move like this. Actually, there are many different rules by which they can move from one queue to another one, right? Another suggestion that I would give, for example, is let's say if the process in the queue with the lowest priority start to age, so they take now too much time to complete, they need to wait a lot of time, then they can move in a queue with higher priority, so they're executed faster, right? So this is the idea of the multi-level feedback queue, that we have queues, but at the same time processes can jump from one queue to another, and that will ensure that we actually use our CPU a little bit more efficiently, okay? Instead of just sticking every process into their queue. As we saw in the previous example, right here, if we use 80% for the queue that holds the fast executing processes, okay, and we have some batch process that is waiting now for too long time, and those 20% of the CPU that are left are not enough, we can easily move them, if we have a feedback queue, to the queue with the higher priority and execute it actually faster to use more resources. All right, and here you can see an example on how this works. So for example, in Q0, right, which is the first Q, we have an RR algorithm that is with quantum 8 milliseconds. So we swap process 8 milliseconds. We can have Q1, which is lower priority, that takes quantum 16 milliseconds, which means we wait 16 milliseconds between processes. And finally, in Q2, we can have first come, first serve. Okay, so let's say if a process goes in first come, first serve, but now it took very long time to execute, it goes to the quantum queue that is with 16 milliseconds execution time. Now in this 16 milliseconds execution time queue, if again there are too many processes that every executes for too long time, right? 16 milliseconds, it might be too long for some processes to wait, right? And if this process stays there more and more and more and more, it never comes a start, then we move it to the faster queue where the processes switch every 8 milliseconds, okay? So you can see the progression, and you can have many queues like this, each of them with lower and lower time quantum, okay? And you can move the process in between them if they have to wait for too much. Okay. All right. So as I said before, in fact, the CPU is not the actual lowest unit in our system, okay, the process running in the CPU, but it is actually the thread, okay. So as I mentioned, we can divide the CPU into different threads, okay, and each of those threads can execute certain queues, right? And we already talked that there are different ways of matching user threads and system threads. Do you remember from the previous lecture what we talked about? So, uh, do you remember what are the types? Let's see if somebody remembers. So first of all, if we have one-to-one, what that means? Exactly. So for each user thread that is created, you immediately create a kernel thread. Okay. If we have um, one-to-many, this means that let's say if we can have many user threads, okay, but we can have only one kernel thread. So whenever this thread is available, we can execute a user thread, okay. So also the third type is actually this one, where we can have multiple user threads and multiple kernel threads. So whenever we have available threads, actually this is also related uh, to your assignment, right? Where we create pool of threads and we simply run tasks on those threads. So this is exactly how it's also happening in the operating systems. You have limited amount of kernel threads, and then you can have certain amount of user threads, usually more, that assess them, right? All right. So actually, the most common model, so normally we either do it one-to-one, or the other two models, one-to-many or many-to-many, we're doing it with another methodology, okay? So if we're using many-to-one or many-to-many, we can do that, and actually there is a library with which you can do that. It is called the process contention scope, okay? This is the library that we're using. And if we're using the one-to-one, this is called the system continuation scope, because wherever user thread is created, we contain exactly the same kernel thread, so they're always matching. And we already talked about the pthread library. So for example, if we want to create threads based on the first methodology, right, we can add them and use this parameter here, pthread scope process, okay, which is going to add threads in the PCS scheduling. If you use the pthread scope system, this is actually going to match the threads from user to kernel one-to-one, okay, and is going to add the threads into the ACS scheduling, okay. The ACS scheduling is also quite popular. Okay, so I'm not going to go over those because we covered threads already. So the next logical thing, guys, that we should be obviously talking about is how we're scheduling processes when we have multiple processors, right? So we already talked how we do that having a single CPU, okay? And now we can talk about having multiple CPUs or having multi-core CPUs, right? These days we just have one CPU with multiple cores, but we can assume that each core is a different CPU, okay? All right. So there are a few ways, right? So the first one is the asymmetric multi-processing. And this is when we assign one process to do, let's say, some system tasks, okay? And we assign the rest to do some other tasks, right? Maybe some user-related tasks. So that way, let's say we can have one processor doing 20% of the, so 20% of all, let's say we have um, 5 processors or 5 cores. If we allocate one, we allocate 20% of the resources for system. Then the rest 4 or 80% we allocate for other tasks. And this is the asymmetric. The symmetric multiprocessing is completely different. So we have the pool of processes, okay, and we try to balance them between the different cores that we have, okay. So we always want to check whether a core is idle or this means nothing runs to that core, and make sure that we assign process to it. But we're going to talk about load balancing as well. Now, it is not that simple as just, making everything equal and spreading the process into the different processors. It is not that simple because so you know that every core has cache, right? So when a process starts running in this core, it checks the cache to see if there is already some information about this process available that will help to speed up the process, right? Okay, so let's think about it. If process A wants to go on the processor X, okay, executes there, now processor X will have cache for this process. However, next time when process A wants to execute, processor X is busy, right? So the load balancer logically would put this process to another core. However, if you estimate the time that it takes for this process to wait, or so the time for this process to wait for being executed on the core X, okay, which is the busy one, might be less than putting it on a completely different core that doesn't have cache, where the process will actually take longer to execute. Okay, you understand what I mean? So obviously we need to take into consideration the cached memory. Not only this, but also if we move the process to another core, this core will also need to create cache. And also the cache in the previous core might become irrelevant if this core is busy all the time with other processes. Okay? So this situation is called processor affinity. Okay? This means that we have process that is very much dependent on a specific core. Okay, so we can check obviously the cache of all of our cores, and based on this we can decide if we want the process to run in the same core or not, if it is worth it or not. Okay, so based on this we can have soft affinity and hard affinity. Soft affinity would mean that if a process run in a specific core, it might execute there next time, it might not. Okay, we're going to try to move it there, but we're not sure about it. If we have hard affinity, this means that the process will take over, it will preempt wherever it is already on that core, and it will take over the core and start executing there since it is more worth it. So you can see that now the rules start to become a little bit more complex when we increase the amount of cores, okay, and when we try to balance the process but also try to keep the rule for the process affinity true, right? Okay, and another type of process dependency, okay, is, for example, let's say if, and this is actually very interesting. So when a process is running into your system, it might read and write to certain memory, correct? So this memory might happen to be closer to one CPU comparing to another. Okay, so obviously now with the single chip multi-core processors, this is very hard to happen, right? But imagine if you have a very big system, maybe a server, maybe a whole wall of servers, right? And you spread the load between the systems, you might have a process that runs in that assess specific memory location, and this CPU that has this memory location might not be available, right? So we want to use another one. However, when we use another one, it will take longer time to access the memory. So in that case, obviously the process will also run longer. So this is just another thing that we also need to put into consideration when we're creating the rules. Okay, so if the memory is too far from a core, it might take longer. It might not, but this is another constraint. So the next thing that's important when we work with multi-core systems, this is the load balancing. Okay, and as I said, the load balancing is making sure that every core in your system is equally loaded, and there are no cores that are just staying in idle state and do nothing. Okay, so there are two techniques that are implemented for load balancing, and those are the push migration and the pull migration. So the push migration, so both of them, they are implemented by specific tasks in your operating system, okay? And in the push migration, okay, the task check the load on each processor, okay? So if we find, for example, that the processor is too busy, okay, or overloaded, we can remove task from this process, okay? The pull migration is another task, okay, that is checking the audio processors, and if it finds processors that are not busy, that are in idle state, then they are going to pull task from the busy processors, okay? So one of the tasks is monitoring the busy processors, and it's used to take it from them and push it somewhere else, okay? So it lives in the processors that are busy. And the other one pulls, so by force takes from the tasks from the other processors. So you might ask, okay, but they're doing the same thing, right? So pushing, pulling doesn't sound the same. The important thing is the action, okay? So in the first case, the action is performed by the busy processor, and in the second example, the task is performed by the idle processor. Okay, so the idle processor initiates the action when we're pulling. This is just in the same way as when we're working with Git, right? So you push your code to Git, you don't ask, you push it, and then you can also pull information from there. Okay, so we already talked about multi-core, but let's see on this image how we can actually implement threads on a single core in order to improve performance. Okay, so I don't know if you heard about memory stall cycle. Have you heard about this? Yes. Okay, even if you haven't heard, it is a very simple thing. So memory stall happens when so first of all, on a single core we can run multiple threads, right? So and we do run multiple threads just because of the process stall. So if you run a single thread, if a process wants to access some other resources but it still stays on the CPU, okay, it is just wasting the CPU, right? You're just wasting the CPU usage, okay? So we call this memory stall. Now, if we run multiple threads, we can schedule those threads, so when one process is stalling or waiting for resources, another one is computed, okay? So we can shift those, and in that way, we can actually make sure that every core is working on its maximum capacity. Obviously, here we have an example only with 2 threads, but in fact, there are way more threads running and making sure to use the CPU in an optimal way. So now, another type of multi-core CPU techniques are those implemented on critical systems. Okay, so if you want to implement tasks on systems that are critical, for example, the ABS system on the car, okay, we need to make sure that we add some time constraints to when tasks are actually executed. Okay, so it is not like in our computer. So the more overloaded the CPU is, the slower the tasks are completed. Okay, in some systems this just doesn't work. And these are the real-time CPU schedulers. So in the real-time CPU scheduler, there is no tolerance for how long the process is going to get executed. We can have a time constraint, and if this time constraint is not met, then the process fails. Okay, it doesn't complete, it is a failure. And as I said, for example, the ABS system on your car, if let's say it is you drive on a frozen road or something like this, you want it to activate as soon as you run into trouble, right? So there you can add some time constraint, for example, of a few milliseconds, okay? And when you test the system, to make sure that every task completes within that time constraint, right? So to do that, you can explore the process and to see the different latencies that can appear while executing a process. Okay, for example, the first one you can measure is the interrupt latency. Okay, which is the time from the arrival of the interrupt. So from the time that the process has been executed, okay, to the start of the routine or the services that are caused by this interrupt, or from the time of the interrupt until the process actually starts. Okay, so far we haven't thought about this. So far we were saying if an interrupt starts, the process start immediately, but in real life this is not exactly the case, and for those time sensitive systems we actually need to measure those latencies. The next one is the dispatch latency, which is the time for the dispatcher to take the current process of the CPU and switch to another one. Okay, so this is the time that we need for the dispatcher to take one process and swap it with another one. Okay, so for time sensitive systems, those times here are very important. Okay, and here you can see in this graph all the times that are involved in a response. Okay, so how long a response takes. So the response time is the time from when the event happened, okay, until the system actually responds. And this is combination of the interrupt processing, the dispatch latency as we spoke, okay. And also once you measure all of those things, okay, based on the process, maybe when you measure the actual system, you're also going to have some deviation. You have many mechanical components and many other things that are taking part. So obviously, not only you need to measure this on the software level, but also you need to measure also the real system. So we know what is the deviation between what you estimated versus the real tech.